Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is my quarantine hair. And I would like to welcome you to the summer 2020 offering of GPU programming for video games. In the next lecture, we're going to look at the high-level shading language, HLSL, as it's called by Microsoft. You'll also see the term CG being used. That was what NVIDIA called it. And this is basically just one of a whole set of different shader languages that are more or less equivalent. In this lecture, we'll look at some general principles that apply to all shader languages, and we'll also look a little bit at shader assembly code. So let's talk about what people mean by the term shader model. Basically, the shader model is defined an agreement of certain kinds of registers and certain kinds of instructions that the GPU will execute, but the exact details of how the GPU executes those instructions is up to that GPU and the driver. So as the programmer, you interface through GPU hardware through an API like OpenGL or Direct3D. Nowadays, we also have Vulkan and Metal. And over the course of the time, GPUs have increased what they do relative to what you wind up doing on the CPU. For instance, early GPUs, at a time where you probably wouldn't even have called them GPUs in the early 80s for your PC, might say, have a command to draw triangles. And over the course of the time, what the GPU could handle gradually sort of moved to the left here. And nowadays, the GPUs basically handle everything. Although there might have been a time where each of the vertices of your triangle could be specified to have a particular color, and then the GPU would interpolate the colors between those for Gaussian shading, but you would still do the computation of those colors on the CPU. Later, more and more of the 3D transformations and the lighting calculations got pushed onto the GPU, so you didn't have to do that on the CPU anymore. Anyway, nowadays you have a bunch of vertices, a big buffer that you send to the GPU, and you also send the information that specifies what vertices and what triangles map to the particular vertices in that list. And that big bunch of vertices is parceled out to a bunch of parallel computing units for computation. Now, this is where we put a kind of shader code called Vertex shader. And when you're writing a vertex shader, you have to remember that the compute unit only knows about that particular vertex. It doesn't know anything about the other vertices. And then all of those vertices are put back together and reassociated with what their triangles are. And then later units will actually figure out what pixels belong to those particular triangles. And then here you'll run something called a fragment shader or a pixel shader, and that's what actually figures out what the color of a particular pixel should be. The term fragment will often be used interchangeably with pixel, and I'll use it interchangeably as well. It's a fragment in the sense that it may not actually become a pixel because maybe it's discarded over the course of the computation, overwritten with a different color value. And also, if you're doing some kind of anti-aliasing, you may have pixel fragments in the sense that you might be rendering the image at a much higher resolution than what's finally displayed, and then those individual pixel fragments are averaged to become the final pixel. In any case, there's other hardware in your card that's responsible for taking the output of these compute units computing your pixels and actually shoving that into the frame buffer memory and doing whatever else you need to do. Needing to do, if you're doing addition for operations of see-through transparency effects or the Z buffer checks, and if something fails a Z buffer check, you might not send that pixel to one of these compute units at all. So these are the two kinds of shader codes we're going to look at. Vertex shaders and pixel shaders. There are also geometry shaders that can actually create new vertices, which vertex shaders on their own can't. We're not going to look at those. And there's also compute shaders that allow more general purpose kind of computation that you might be doing some sort of physics calculation or artificial intelligence calculation, or maybe some sort of audio digital signal processing. But for sake of time, we're not going to look at those in this course either. We're just going to stick with the vertex and the pixel shaders, because those are going to be common to every 3D game. So coming from a more conventional programming point of view, something that takes a while to get used to is that the main element of operation in our graphics calculations are operations on floating point numbers. In fact, integers don't even exist before shader model 4.0. And bitwise operations hence don't exist either. Now you'll see for most of what we do, we don't actually need integers. But in the places that you are thinking about doing something with integers, if you're in Shader Model 4.0 and earlier, well, you're stuck with representing those integers as floating point numbers, however strange that might be. Now, in earlier GPUs, you had all sorts of different floating point formats, and you sort of do nowadays. We'll look at that a little bit when we come to it. But for the most part, you could just think about these things as standard 32-bit IEEE floating point integers. Again, earlier GPUs would have all sorts of weird hybrid formats. We'll also have things like floating point values in either 4x4 vectors. And what we'll see is that there's not really necessarily a fixed convention in the shader code itself about whether these should be thought of as row vectors or column vectors. There are these 4-number things that, depending on how you arrange the computation in your shader code, you can interpret them as columns or as row vectors. But the data type itself doesn't have that information built into it. We'll also have 4x4 matrices that we've seen are the basic building blocks of 3D graphics operations. And then there's also smaller versions of these. So you can have a 2-dimensional vector or 2x2 matrix, or a 3-dimensional vector or a 3x3 matrix. So this especially gets weird later when we look at post-processing effects, where you actually snarf the whole screen as a texture and re-render it just as a rectangle. And you can do things like blurring effects. If you're used to doing usual image processing, you're used to writing things like I+1, where I is some integer index. Well, here we won't be doing that. We'll be taking some coordinate and adding a floating point value to it. So that takes a while to get used to. Anyway, those kind of post-processing things are things we're going to look at later anyway. So there's 3 main types of data we're going to look at. One that they call per instance is, for instance, the particular vertex that you're processing at that moment. So you have an object consisting of 1,000 vertices. You'll write a piece of shader code, but that piece of shader code doesn't know or care which particular vertex it's getting. It just knows that its job is to process that vertex. Now, coming out of the vertex shaders, once those are reassociated with particular triangles, there will be interpolation hardware in the GPU that will generate all of the data that needs to be passed into the pixel shaders. So that might be an interpolated normal vector to do Phong shading, aka per pixel shading, or maybe you're doing Garot style shading where you've computed a light value in the vertex shader and you're now interpolating that to put into the pixel shader. And certainly if you're using textures, that's something that needs to be happening on the pixel shader side to look up the appropriate texture color value for the individual pixels. So in that case, your vertex shader will return some texture coordinates that get interpolated by the interpolation hardware and then passed into the individual compute units that are running your pixel shader program. And then you also have data being passed in by the API that applies to, say, every vertex you're computing, which would be something like the position of a light or the various transformation matrices, worldview projection, or perhaps pre-multiplied combinations of those vertices that apply to all of the vertices that you're computing for a particular object. These are usually referred to as uniform variables. So shader code is intriguing because it'll have specific assembly instructions to do some fairly specialized things, such as dot products or exponentials. Interestingly, there's no specific instruction to take a square root, although there is a specific instruction to take a reciprocal square root. This makes sense when you realize that multiplying by the reciprocal of a square root is something that you need in order to normalize a vector to have unit length, and that's something you do a lot when doing lighting calculations. So if you do want the square root, your best bet might be to use this reciprocal square root of operation and then take its reciprocal. And then you'll have trigonometric functions that are built in. Usually for general rotation, you will pre-compute this on the CPU because you'll create a matrix that's applied to all of your vertices. But there are times where you may be needing to use trigonometric functions inside the shader itself. Now, one of the most important aspects of a GPU is its ability to swap data around in these 4 tuples, these units of 4. So you could refer to these individual data values as XYZW, or you could also refer to it as RGBA. The GPU itself doesn't care. This is just a nomenclature for the user.
X corresponds to R, Y to G, Z to B, and W to A. Although, of course, we'll want to use XYZW when we're talking about coordinates and RGBA when we're talking about colors, the GPU doesn't really care. This is just a nomenclature for the human. It just does everything in groups of 4. The idea of swizzling is that as we're doing operations, in addition to whatever operation we're doing, we can also rearrange these elements of the 4 tuple. You could swap X with Y or W with Z. And you could also play games where only some of the components of your 4 vector are getting assigned and the others are being left alone. Or you can take one value, say it's W, and splat it. You can then write it to all 4 of the vectors. It's fairly flexible, and the main important thing about the GPU is you can do this with everything in every instruction. And you don't have to have specific code to do these rearrangements the way you would if you're writing it on some more general purpose processor. Also, if you want to take a minus sign of something, that's also just built into the opcode. You don't have to do that in a separate instruction. This is one of the main things that makes the GPU a GPU. And it's one of the main reasons that other things that try to do the job of a GPU just inherently don't do it as well. So although people have developed all kinds of hardware to do specialized tasks, like PhysX created a piece of physical hardware to do physics computation, that didn't last. Somewhere around a dozen years ago, I went to the Game Developers Conference in San Francisco, and there's a company selling a plug-in card to do artificial intelligence calculations. That didn't catch on either. In the mid-90s, when I first got into using computers to digitally record and manipulate music, I bought a sound tool system that at the time was incredibly expensive. I got a deal on it because it was a display unit at the store, so they were selling it for a little cheaper than usual. But it was still well over $1,000, and it was just a 2-track recording playback system. And later, DigiDesign, now Avid, would create all sorts of plug-in cards for Pro Tools that would have custom DSP chips for audio. And companies like Universal Audio still make things like that. But nowadays, your raw CPU is just so fast that it's reasonable to do those kinds of computations just on the CPU. So Billie Eilish and her brother Phineas can make a best-selling award-winning album on a MacBook just using Logic Pro X. And nowadays, for so many things, it just doesn't make sense to have expensive specialized hardware when generic CPUs progress so quickly and are reasonably priced because they're mass market items. There's one spot where it really still always makes sense to have a custom piece of hardware, and that is the GPU. Now, I should mention that the assembly code examples I'm about to show you, this is actually fairly old. These are examples from GPU Gems 2, but all of the basic ideas will also apply to modern shader assembly code. Okay, so the main job of the Vertex shader is to do the transformations from the first few lectures where we talked about transforming 3D coordinate spaces and also projecting 3D coordinates onto the two-dimensional screen. So here, different compute units will be assigned different vertices to process. These usually start in the model space used by your 3D artist. And these will also be taking your texture coordinates. Now, although we'll be transforming your vertex positions quite a bit, here I'm using a column convention, but you could also imagine using a row convention. The texture coordinates most often are just passed directly through because the texture lookups won't actually happen until we get to the pixel shader. Now, if you weren't using textures for the colors, you might have colors associated with the individual vertices being interpolated for grow shading. You'll only really see that in some extremely old 3D games. Even early on, people very quickly switch to using textures for colors. You will often have people use the color slot in the vertices, but it's usually used to contain some other kind of information beyond, say, diffuse colors. And then you'll have certain inputs that are common to all of the vertices, and these might be things like your 4x4 transformation matrix for your vertices. We often refer to those with the uniform keyword. Your vertex shader is going to spit out some things, say color. Maybe it's going to be transformed normal vectors because you're going to actually be doing the lighting calculations in the pixel shader per vertex. Or maybe you're doing grow style shading where for each of the vertices you have actually computed a light value, and that's obviously going to save a lot of computation. Either way, whatever's coming out of the vertex shader gets interpolated to create the inputs to the pixel shaders. Early GPUs would often have dedicated Vertex shader units and pixel shader units. You would have a lot more pixel shader units than Vertex shader units because any given triangle is going to generate a lot more pixels on average than just the 3 vertices. And the information coming out of those Vertex shaders is not directly passed to the pixel shaders. It gets interpolated over the triangle first. So this is the description of a Vertex compute unit under Shader Model 3.0. Again, how this is exactly implemented on any given GPU is up to the GPU. Modern GPUs typically have a unified compute architecture where any given compute unit can serve as a Vertex shader or a pixel shader, and it's up to the card and the driver to figure out how it wants to parcel all of that out. So everything you see in here is one of these 4 vectors. Either it's an XYZW or an RGB alpha, or those are just names. It can also represent other kinds of data. So you'll have a certain number of general purpose registers for your computation. If you're writing shader assembly code, you're thinking of those yourself. Nowadays, usually you will use some higher level shading language, either HLSL specifically or another high level shading language, one not necessarily actually called HLSL. And you'll define some variables and the compiler will decide how to allocate the registers. But this is it as far as memory goes. Shader code's very simple because the compute units themselves are very simple. There's no malloc in shader code because there's no heap to allocate memory on because there's no memory for a heap. Similarly, there's no stack. There's no recursion in shader code. You can't have a function call itself. All functions are basically inlined. When you call a function, it's not like you're allocating space on a stack to pop parameters onto along with a return address and then pop those back off. There's no stack. It's just these registers and that's it. Now there's a bunch of registers associated with constants. These are for what I've been calling the uniform variables. These are things like positions of lights, colors of lights. They're things like the elements of a 4x4 transformation matrix that you're applying to your vertices. And remember, all of these registers, whether it's a constant register or one of these dynamic variable registers that you can use in your computations, all of those are by 4. So whether you're storing your information this way or whether you're storing your information this way, any 4x4 matrix is only going to take up 4 of these constant registers. Now, under this shader model, you do have some fairly specific things. Here we have an output register for fog. That's fairly specific. You also have here some specific output registers associated with particular diffuse or specular color computations. We're not really going to use this kind of functionality because we'll want things to be more general, but that kind of facility is out there. Now we'll have some input registers that from the point of view of the compute unit, it has no idea where it actually came from. There's someplace further upstream on the card that's deciding what vertices are getting passed to what compute units. When you're writing your code, you imagine this stream of Vertex data coming in, and your card will run a piece of code on it to produce various outputs. But again, the outputs that you compute aren't directly used by the pixel shader. They get interpolated first for all of these pixels that are being created. So typically you will output a position that's locked to a hardware register that has a particular meaning. This is what other parts of the card might use to figure out as part of a Z-buffer check to see whether the pixel shader should be run at all. Here we have a texture coordinate, and sometimes we don't actually put texture coordinates in here. Sometimes we'll put some other kind of information, say normal vectors, because we want to actually do the lighting calculation of the pixel shader, and we're repurposing that texture register to hold that normal information because then we can take advantage of the coordinate interpolation hardware that's built into the GPU. So let's take a look at some shader assembly code. This particular example is from Stanford, and it's a fairly old example. This is fairly old shader code, but you'll see the exact kind of instructions in modern assembly code. Now, in this class, we're not going to write assembly code, and even in professional context, you very rarely want to write. In fact, you never want to write shader model assembly code from scratch. You may have situations where you will look at the compiled output of one of your shader compilers, and you might tweak the assembly code. More often what you'll do is you'll use the created assembly code as guidance to go back and tweak your higher level shader code to try to give hints to the compiler that it wants to do something more efficient. Now, usually trying to game out the compiler and figuring out how to twiddle your code to make the compiler make more efficient code, that's usually a losing battle because it's specific to both the architecture you're targeting and the compiler itself, and later versions of the compiler might do things differently. And as Mike Acton, the engine developer at Insomniac Games, who I think now is actually working with Unity on their new data-oriented computation framework, is fond of saying, the space of optimizations that the compiler can come up with and handle is fairly small, and they're fairly brittle. If you just make small changes in your code, the compiler doesn't see something anymore. Anyway, let's take a look at some shader code. And here you'll see the beauty of swizzling. So here's an example of computing a dot product. The dot product can be written in terms of the determinant of this matrix where I, j, and k correspond to unit vectors in the x, y, and z direction. The first coordinate will have the y coordinate of r0 multiplied by the z coordinate of r1, and we want to subtract, going the other direction, computing the determinant, the y-coordinate of r1 and the z-coordinate of r0. So if you look at the computation here, what's being put in r2 is what's being subtracted. So that's this r1.y and this r0.z. So here we've got r0.z and r1.y, and that's going into the x-coordinate. All right, so what goes in y? Well, eventually we're going to subtract r0x and r1z. So that we see here, r0x, r1z. What are we going to subtract in the z-coordinate? Well, we're going to subtract, going this direction, r1x, which you'll see here, and r0y. And that goes in the z-coordinate. So those are the things that are going to get subtracted on this next line. Remember, this minus sign, that happens free on the GPU. We don't have to waste specific instruction to do that negation. That's a bit in the opcode field of your assembly instruction. Now, as I'll talk about in a second, these assembly instructions are probably not actually what's being executed on the GPU. The GPU is actually probably running some even more primitive kind of assembly code. There's usually a pre-compilation stage run by the API and driver for your card that will take this kind of assembly code and boil it down to whatever is actually running on the GPU. And the thing that's actually running on the GPU, quite often, not only do you not want to know about it, because it'll vary from GPU to GPU, quite often you can't know about it unless you've signed a non-disclosure agreement with the manufacturer of the GPU. NVIDIA and ATI will often consider that their special sauce. Okay, so what about the stuff you're not subtracting? That's what goes in here. Although this is a multiply operation, this is a multiply and add operation. So this is the kind of thing that shows up on a digital signal processing architectures, this multiply and add, or DSPs will also often have a multiply and accumulate instruction. So this is the stuff going from upper left to lower right. So in the first position, we have R0Y and RZ1. In the second position, taking this matrix determinant, we have R0Z and R1X. And I'm going through this in a pedantic amount of detail because it's easy to get lost here. Okay, so what about for our Z component? Going from upper left to lower right, I've got the X coordinate in R0, I've got the Y coordinate in R1. And that's getting shoved into Z. So all of the upper left to lower right stuff is getting multiplied here, and then the lower left to upper right computations, those are getting multiplied here and subtracted as part of this instruction. So notice in just two of these assembly instructions, we've implemented a cross product. Now just think about how complicated this would be if you're writing it in some other more generic assembly code. The swizzling here gives you all kinds of power. So you might also ask, what happens with W? Well, there's not a whole lot interesting here going on. So I guess here we're taking the two W components and multiplying them together. And then in the next line, we're subtracting it. So I guess 0 comes out in the W spot. I think the assumption here is that it kind of doesn't even really matter what's happening in the W slot. So this is just the easiest thing to do, and that's fine because the only thing you really care about out of this cross-product calculation is what's happening in X, Y, and Z. Suppose we wanted to normalize a vector to have a length of 1. This is a thing we often have to do in lighting calculations. So the first thing we're doing here is taking a dot product of R1 with itself. That does this calculation here of adding up the squares. As you might guess, there is also a DP4 instruction that includes the W component. And the way these opcodes work, as you can guess from earlier, is that the result is stored in the first register here. So this is just giving us a number in the dot product, so we have to specify where it goes. And here we're just going to put it in the W register to have a place to put it. And here we're going to take the reciprocal square root of this W component, and we're going to stick it back in the same spot. So that does the 1 over square rooting. And incidentally, it doesn't change any of the others. So it's just going to write this in the .w component, but it's not going to change x, y, or z. And then in the next line, we're taking register 1. We're going to multiply each element of register 1 by the scalar that's in register 0.w. That's this reciprocal square root. And then we're going to store the result of that multiplication into R0, but only in the x, y, z coordinates, leaving the w component there unchanged. So the w component is going to have whatever the normalization factor here is if you need it for somebody else. I can't think of a situation where you actually need that value after the fact, but in case you needed it, there it is. So just 3 instructions, and we've managed to normalize that vector.
So when programmable graphics hardware first came on the scene, people would program these GPUs in their raw assembly language, and that was a big mess. It was very much like the situation of developing video games in the 1980s, when people would have to write assembly code for the 68000 or the 6502 or the Z80. But the kinds of, quote, assembly instructions, unquote, I'm showing you here aren't really like that. These are more like Java bytecodes or C#.NET bytecodes. Most likely, the GPU isn't implementing those instructions directly. They probably represent something more like an intermediate stage that the driver is compiling down to an even more primitive set of assembly instructions. So although counting these shader model instructions will give you a rough sense of computational complexity, it's not an exact calculation, because exactly how these instructions are implemented, how many cycles each takes, will change from GPU or may even change from driver to driver.
So let's look at a more complicated example of a full shader. I'm not going to go through every single detail here. I just want to give you a sense of things. We'll look at how to do these kinds of calculations in a higher level language later. So here we have our vertex coming in. And to do the 4x4 matrix multiplication, we'll do 4 dot products, where each of those dot products is a 4-component dot product. And so here, C0, C1, C2, C3, remember each of those has 4 values in it. That combines to form my main transformation matrix. In order to transform the normal, we'll actually need to use the inverse transpose matrix. Now, I haven't shown you why that is yet. We'll leave that for a future lecture to explain the math about why that is necessary. I've shown you how to transform 3D vertices, but I haven't yet really shown you the math of how to properly transform 3D normals. We'll do that in another lecture. Okay, so the lighting calculation that's actually done here is an older style that includes the diffuse component that we've talked about already. And here it also includes a generic ambient term. That's just sort of a number we add in there to represent general light bouncing around the scene. Nowadays, we have more sophisticated ways of handling that. This is also illustrating an older graphics model using something called blend-Phong specular. This is not a physically plausible model. It doesn't have Helmholtz reciprocity, so you can't change the eye and the light source and get the same answer. And it also isn't energy conserving, but it was computationally inexpensive and good enough to make games for quite a while. Nowadays, people will generally use a more sophisticated specular model called the Cook-Torrance model, and I'll actually spend an entire lecture on that, so we'll look at that another time. The details of this, again, aren't important. I just want to give you a general feel. So here we have a couple of these multiply and add instructions that add up the various lighting effects to produce the final output that is then sent to the interpolation hardware that creates values that are sent to the pixel shader. Now, this is a per vertex lighting scheme indicated by this code. A per pixel lighting scheme would have these calculations done in the pixel shader and not here in the vertex shader. So those are examples of a vertex shader. The pixel shader, aka the fragment shader, is the code that computes the final color value that's written to the screen. So if you're looking up anything in a texture, you want to do it here. And so things like texture coordinates aren't just used directly out of the vertex shader. The vertex shader might compute certain things, but those are only things computed for each vertex. And then it will take values and interpolate between them before it takes a particular value and parcels it out to the various compute units that are running the pixel shader code. Now, the registers that are attached to the interpolation hardware, those don't necessarily have to be given texture coordinates. The vertex shader can put whatever numbers it wants in that slot, so you can use that for other stuff, and we'll see many examples of this. Now, in addition to outputting color, and that might include alpha, transparency, or stenciling information if you need it, the pixel shader can also deal with depth values. Most of the time, this isn't something you as the programmer need to deal with explicitly. This is handled automatically by the GPU behind the scenes, but it can use that to do Z-buffer depth tests and other things. So there's a general trade-off in quality between doing calculations on the vertex shader side and doing calculations on the pixel shader side. Usually calculations done on the pixel shader side are going to look better, but certainly trying to do whatever you can get away with on the vertex shader is going to be less computationally expensive. So we looked at an example high-level computation model for a vertex shader. Let's do the same thing for the pixel shader. Again, these registers are all the scratch space you have to work with. There's no memory where you can pop things onto a stack, so function calls don't involve pushing parameters on a stack the way you would get with a language like C or Java or anything else nowadays, or most other things really. And there's no malloc, there's no heap to allocate memory on. This is all you've got. All of these things, again, are 4 component vectors, either XYZW, or especially now here on the pixel shader, it might be RGB alpha, depending on what you're doing. So we do have constant registers that are pieces of information that are the same for all the pixels being rendered. Say the positions and colors of your lights if you're doing per vertex lighting, aka Phong style lighting instead of Grow per vertex lighting. The one thing that's new here compared to the vertex shaders is we have hardware mechanisms that go out and talk to the parts of your video memory that are storing textures. And these are linked to interpolation hardware. So if you have the appropriate API settings to do bilinear interpolation, the hardware will do that for you when it does the texture fetch, versus say if you have the API set to tell it to do nearest neighbor interpolation. And your job as a pixel shader is to figure out what the color and depth of the pixel are. And the depth is usually handled automatically, but the color is a thing that you need to explicitly code up in your shader. So the coolest effects generally have their basis in the pixel shader because you can get a lot of details here. Anything you're doing with textures, even if it's just a basic diffuse texture, you have to do in the pixel shader because that is a per pixel thing. And certainly if you're using normal maps to get these interesting, rough, bumpy looking effects without adding geometric complexity to your original vertex mesh, that has to be done in the pixel shader. But even if you're not using normal mapping, if you are doing per pixel lighting, you quite obviously need to do that in the pixel shader. So that is expensive. If you're doing per pixel lighting, typically you'll take normal information from each of the vertices, use the texture coordinate interpolation hardware to interpolate that and pass that in the pixel shader, and then you do a per pixel computation using those interpolated normals. Again, the hardware just sees numbers. It doesn't know that you're using that texture coordinate register to store normal information instead of texture information. Anything you're doing with shadows will by default need to be a per pixel computation. And later in the class, we'll look at the details of using cube maps to reflect light from the general environment. That's something you would have to do in the pixel shader. So per pixel effects are more computationally intensive than per vertex effects, but they can look pretty cool. So as I mentioned before, we won't actually be writing assembly language in this class, although we might on some occasions look at the assembly code output created by our compilers. we'll be using a particular shading language called CG. It's also known as HLSL, High-Level Shading Language. HLSL was the Microsoft term and CG was the NVIDIA term. Way, way back, these did start as being different things, but they basically converged and became the same thing. Nowadays, nobody really says CG, they just say HLSL. And the term high-level shading language, you could use that in two ways. You could say high-level shading language in the general way of there's a bunch of shading languages out there that are high-level, and then there's also the specific, quote, high-level shading language, unquote, that was defined primarily by Microsoft, but also essentially by NVIDIA. And this sort of higher-level language is obviously a lot nicer to work with, but it's also not really that far removed from the underlying assembly code it produces because the processing units themselves are fairly simple things. So HLSL/CG is not the only game in town. OpenGL had GLSL, which looks fairly similar. Nowadays, Vulkan and Apple, for some reason, insisted on doing its own thing, I guess because it's Apple. They should have just gone with Vulkan and been done with it. Anyway, Vulkan is sort of the successor to OpenGL. But all of these shading languages are really fairly similar because whatever GPU you're using, they all have sort of the same underlying basic shader model, 3, 4, 5, 6, whatever. And a sophisticated engine like Unity will let you code your shaders in something like HLSL, and then if it needs to, it will translate it into these other languages for you. And that's how you can write your thing, quote unquote, once in Unity, and then deploy it for Mac, Windows, Linux, yada, yada, yada. So if you are not taking GPU programming for video games with me in the summer 2020 semester, you can check out here. But if you are taking it, I would like to make sure you are watching these videos. So please go to Piazza and respond to an appropriately titled post that I'll make with two things. One, the number of letters in your last name. I just want to make sure that you're watching the video and not guessing how to respond based on what other students are writing. And also when you do this, don't write number of letters in my last name is. This is just between you, the person watching the video, and me. So the main thing I would like you to do is give me your thoughts on a tiny clip of this video of an interview of music educator Rick Beato by Spitfire Audio co-founder and media composer Christian Henson. If you're into music, I would recommend watching the whole thing, but for the purposes of this assignment, I just want you to watch from the 37-minute, 8-second mark to the 38-minute, 48-second mark, in which Rick and Christian discuss education in the time of COVID-19. And just give me a few sentences with your thoughts on their discussion. What do you agree with? What do you disagree with? What lessons can be learned? Just generally, what's your impressions?